Hi guys, welcome back to AP Chemistry. I hope you had a good winter break. We are jumping in to Unit 6. Our Unit 6 is going to be Thermodynamics. And remember, we only have 4 units this semester, 6, 7, 8, and 9. Okay, so we're ending it off. Some of these are going to be some harder units. Thermodynamics is not going to be one of them though. Thermodynamics is typically an easier unit. There is a lot of math in this though. So if math is not your strong suit, this may be where you want to study a little bit more. Okay, so starting off with some vocabulary, we'll have endothermic and exothermic. We'll have the 4 laws of thermodynamics, talk about calorimetry and specific heat, enthalpy, Hess's law, entropy, Gibbs free energy, and spontaneity. All right, so hopefully a lot of this you've heard before in 10th grade chemistry. You should have, I think, talked about all of this, if I'm being honest. Nothing here should really be new to you, but we'll jump right in. Okay, so endothermic versus exothermic. Remember, endothermic means that heat is absorbed by the reaction. You're taking heat in, okay? So if heat is absorbed by the reaction, it's lost by the surroundings. Be careful with those differentiation, okay? So heat is going into the reaction because you're breaking bonds, okay? If heat's going in, enthalpy is positive, okay? If you have positive enthalpy, if it's going in, it's a reactant. So whenever you write your reactions, it's reactant plus heat goes to product, okay? And remember on our graphs, that means that our reactants are going to be lower than our product. It's going to have an upward climb. For exothermic, it's all the opposites. Heat is released by the reaction. It is exiting. Okay, your bonds are forming. Enthalpy is negative because it's exiting. And your heat is a product, right? So the reaction is reactant equals products plus your heat. Okay, and remember if heat is exiting, your exothermic is going to have a downwards climb. All right? So what you should be able to do first is just look at different statements and tell me if they're endothermic or exothermic. Okay, so if we have hydrogen peroxide decomposing, okay, if it's decomposing, we're breaking bonds, that is endothermic. For oxygen and hydrogen gas forms water, right? If we're forming water, we're making bonds. So that is exothermic. All right. For water freezes, if our water is freezing, right? If we're going from, remember if we have phase changes, if we're going down the phase change chart, if it's freezing, that's exothermic. Going up is endothermic. Okay. So this is going to be exothermic. Sublimating is going to be endothermic. Okay, think about if it needs energy in or out for those, right? To freeze something, it's going to release energy, but to melt it, you have to put energy in. You have to put energy into the ice to melt it. All right, and then these last 4 are looking at numbers. If our heat is on the right side, on the products, that is exothermic. If it is negative, it's exothermic, because it's exiting. If it's on the left side, if it's a reactant, it's endothermic. And if it's positive, it's also endothermic. Okay, so you should be able to do that with statements. Make sure you understand the phase change graph with it. That can be confusing to some people. But think about if energy is going in or if energy is going out. Okay. We can also answer a question like this, right? If we have this diagram below with 2 reaction profiles, right? We have 2 paths. One is solid, one is dotted for the decomposition of XY2. Which of the following best describes the flow of heat when you have 1 mole of XY2 decomposing? Okay. So A says 50 kilojoules of heat is transferred to the surroundings. Well, first let's look at this graph, right? Our reactants are here. Our products are here. And then we have 2 activated complexes based on your path. Okay, so remember heat transfer is not based on the activated complex, it's just from the reactants to the products. And that number is going to be 50 kilojoules. Okay, so it's going to be 50 kilojoules, but is it transferred to the surroundings or from the surroundings, right? If it's a positive number, that means energy is going in. It's endothermic. So we're going to take it from the surroundings. So it's B. Okay, so be careful with wording there. All right, so talking about different types of heat transfer, right? These ones, I think you actually learned these in middle school as well, but you have convection, conduction, and radiation. Remember, convection is when you have the cycling, when like liquids where the hot particles rise and the cold particles fall, right? If you're boiling water, you're gonna have the convection there, the particles cycling. If you're thinking about like AC in a house, if you live in a 2-story house, if you have the bottom floor as a hotter temperature than the top floor, it'll cycle there. The air from the bottom floor will go up to the top floor and vice versa, because hot air rises. Think about a hot air balloon. Okay. With conduction, heat is transferred between two objects with physical contact. Right? If you touch a hot spoon, it's gonna be hot to you. Radiation is without physical contact. So things like the sun, or if you have one of these electric stoves, that's by radiation. All right, so talking about calorimetry, right? Calorimetry goes based off of the first law of thermodynamics, which is the amount of energy leaving a system is equal to the amount of energy entering a system, right? You might have also heard about you can't create or destroy energy or particle matter, but you can convert it, you can transform it. That's the same thing here, okay? So what we're talking about is the heat gained, where Q is the energy or heat, right? When that energy is gained, it's equal to the negative amount of the energy that's lost, okay? So if I have a pot of water on a stove, the amount of energy, let me do, like we did this in advance. We had a Cheeto that was burning, right? The amount of energy that Cheeto gave off is equal to the amount of energy that the water took in. Okay, so that's what that's meaning. And then just really quick, some vocabulary for systems. We have open and closed systems. Open system is what it sounds like. It's an open container. Both matter and energy is being exchanged. They can move around. A closed system is not open. It's literally a closed container where the matter can't change, but you can have energy move around. All right. So for calorimetry, it looks something like this image on the right. This is a paper cup calorimetry. If you were in on-ramps, you actually did this experiment with, I think it was ammonium chloride and water. But what's happening is you have a reaction vessel that minimizes heat loss. That's why we use styrofoam cups, because they're insulators. And we have some sort of cap on it. And we can measure the temperature change of the water. So we have a thermometer that goes into water to measure the temperature change of the water. And by that, we can determine how much energy was released or absorbed by the system, right? So from the change in the water, we can determine the energy absorbed or released by whatever we're measuring, whatever we're doing. And we're going to use this equation here. Q equals MC delta T. It's also known as the MCAT, because that delta looks like an A. Okay, so remember, Q is the energy transferred, M is your mass, C is your specific heat capacity that's given to you, and delta T is a change in temperature. Remember, change is final minus initial. One thing to note here is if you're dissolving something, so on ramps you did that ammonium chloride in water, advanced you did not do that, you did a Cheeto chip. But if you're dissolving something in water, you're going to add the mass of the water with the mass of the compound. Okay, so that'd be for the M term there. But if you are not dissolving, if you just have a chip burning or something's burning, it's just the mass of whatever you're burning. All right. So for specific heat, the definition for this, remember the specific heat is the amount of joules of energy to raise the temperature by 1 gram of substance by 1 degree Celsius. Okay, this is unique for every substance, And it's different for states of matter as well. So here we have the numbers for water and ice. So this is both H2O. But for water, so this should be an equal sign, not a minus. Water is 4.184, ice is 2.090. So two very different numbers, even though it's still H2O, it's different forms of it. Okay, so let's do some practice with it. How much energy is needed to warm up 300 grams of water from 10 degrees Celsius to 37 degrees Celsius if the specific heat is 4.18? Okay, so we have our pieces, we're looking for energy. So we're looking for Q. So Q equals, we have the mass of 300. We have the specific heat of 4.18. And then we have our temperature change, 37 minus 10. Right, the final minus the initial. And if you plug that in, do the math for that, you get 33,858 joules, or you can also report this as 33.858 kilojoules. The question was not specific what to report it to, so either of those are acceptable. Okay, so this is how much energy the water gained because it increased temperature. So how much energy was lost from the torch? So the torch Q is equal to the negative, so negative 33,858 joules. It's the negative of water. Okay, I'm going to leave this one for you guys. So try to work through this. You should get your second temperature 13.24 degrees Celsius. Okay, but work through that, make sure you get that answer. All right, and let's work through this one together as well. Okay, so if we have an experiment where a student mixes 50 milliliters of sample of 0.1 molar AgNO3 with 50 milliliters of 0.1 molar NaCl at 20 degrees, which of the following is the enthalpy change of the precipitation reaction if the final temperature is 21 degrees? Okay, and it tells us assume the total mass is 100 grams and the specific heat capacity 4.2. Okay, so it tells us the mass, it tells us the C, and we have our delta T. Okay, so let's go ahead and put our numbers in. We have Q, our mass is 100, our specific heat is 4.2, and our change in temperature is 21 minus 20. And from that you get 420 joules. Notice here none of our answers are in joules, or in kilojoules. So that's also equal to 0.420 kilojoules. All right, so which one matches that? And really quick, we have two than the 0.42. To make sure we have the right one, our temperature went from 20 to 21. We're increasing the temperature. That means it is endothermic, so our Q should be positive. Okay, so our answer here should be C. Right? Okay, so talking about enthalpy, right? Remember, enthalpy is the amount of energy transferred. We have a couple different enthalpies. We have enthalpy of fusion, so H, FUS, is going from solid to liquid, so the melting or freezing. Enthalpy of vaporization, or heat of vaporization, so delta H VAP, is for condensing or evaporation. Okay, those are shown here on the graph. And remember, if you are in a phase change, so we use a Q equals MC delta T, that equation we did, when temperature is changing. Those are those slanted parts. If you're in a phase change where it's flatter, use this equation instead. Use the Q equals M delta H. Okay, M can either be mass or moles, so be careful about your units for delta H or for Q. Okay, so make sure you watch your units for M. Okay, so if we have this question here, if we have 10.11 moles of newly formed steam is immediately frozen solid. So we have a gas going directly to a solid. how much heat is lost to complete this. Okay, so we're given moles, and we're given a bunch of different parts of water. Okay, so if you think about it, if we look at this graph, let me zoom in real quick. We're starting as newly formed gas, so we're right at the bottom there, and we're going to, it said immediately frozen solid. We're going to here. Okay, so we're passing through a few different parts. We need to do 1, 2, 3 steps. Let me do third one different color, and we'll actually do these in different colors. There. Okay, so we have three different steps. So our first step, we are going to do Q equals M delta H of vaporization. Our delta H of vaporization has units of moles, which matches with what you have, so that's good. So our M is our moles, 10.11, times our delta H, which is 40,700. Okay, our second step is Q equals MC delta H. Okay, be careful here, our C is in grams, but we have moles. So to find grams, we need to do our 10.11 times our 18 to find the number of grams that we have. Okay, so that should give our 18.01, I believe it is, for water. Let me do the math real quick. So 10.11 times 18.01 gives us a mass of 182.08 grams. Okay, so for M here, we're going to use our mass. So 182.08 grams times our C. So in this step here, for step 2, we are as a liquid. So we need a C of liquid water. So 4.18. And the change in temperature, water, or so that's given on the graph for this one. But remember, water goes from 0 to 100 when it's going as a liquid. So it freezes at 0, boils at 100. So 100 minus 0 is going to be 100. Or sorry, this is final minus initial. So it should be 0 minus 100. So it's negative 100 there. Okay? Or truthfully, all of these should, let me just do this as positive, because all of these should be negative numbers when it comes to it, right? Because you're going in the direction of the left direction, we're releasing energy. So all of these should be negative overall. Okay, and in the third step, our Q is MC, or sorry, not MC delta T, it's M delta H. So our M delta H, we're going with moles again, 10.11 moles. And then for delta H here, we're doing it for fusion. So that's our 6,020. Okay. And if we do the math, we add these all together. So figure those out, then add them together. We get 548,469 joules. So it's that many joules lost, or you can represent it as negative 548,469 joules for Q. Okay, so when you're doing an enthalpy question like this, where you have something go between phases, you're going to do each part separately, then add them together. And remember, if you're going to the left, you're losing energy. Going to the right, you're gaining energy. So left is negative, right is positive. Okay. All right, and then for this question here, we have a 2 mole sample of C2H5OH undergoes a phase transition illustrated in the diagram. The molar enthalpy is, so delta H vaporization is 38.6 kilojoules per mole. Which of the following identifies a change in enthalpy for the phase change? So first, let's look at the phase change. So we are going down. It's going from a gas to a liquid. Okay, so gas to a liquid, that's condensing. So we're going to have a negative number here. So enthalpy is going to be negative because we're condensing. Okay, now looking at our number, we have our delta H was given as 38.6 kilojoules per mole. But we said we had 2 moles. Okay, so if we have 2 moles and we're looking at it for this delta H value, we need to divide the delta H by 2. So we would get the 19.3, and we know it's a negative number. All right. Okay, so for calculating enthalpy, if we're given numbers in a table, right, we remember this table with the enthalpy values, there's 2 ways to do it. You can do delta H is equal to the bonds broken minus the bonds formed. So the reactants minus products, if you're given bond values like you have in the table here. Okay. You can also do it as products minus reactants if you're given compound values like you have down here on the bottom right. Okay. This equation, the one on the bottom, is given on the periodic table, or not periodic table, on the formula sheet. The one on top is not given. Okay, but you should still know that. So if you're doing bonds, it's reactants minus products, but that is not given on the formula sheet, so be careful with that. Okay, and remember, for if you're doing bonds, elements have a bond enthalpy of 0. So if you just have aluminum that has a bond enthalpy of 0, it's an element, it does not have a bond. Any bonds, including diatomics, do have a value. Okay, and the stoichiometry does matter. Same thing for down here with the products minus reactants if you have compounds, except diatomics are also included in having a value of 0. All right, so be careful with that. Sometimes they'll give you multiple different values, but they won't give you a value for, like if oxygen, if O2 is in your reaction, they just won't give you that value because it's expected to know that that's 0. Okay, so let's go ahead and do these 2 real quick as examples. If we have this reaction, H2 plus Cl2 goes to 2HCl, and we have these bond enthalpy values, we need to find the delta H. Delta H is our sum of our reactants. So let's do the reactants first. So we have 1 HH bond, so 432, plus 1 ClCl bond, 239, minus our products. We have 2 of these bonds, so 2 times 427. Okay. And we should get here negative 183. The units are given in the table, kilojoules per mole. All right. If we're doing with compounds, it's going to be the same thing, but products minus reactants. So delta H equals, the stoichiometry is 1, 2, 1, 2, 1. We only have 1 of each. Okay. So it's just going to be straight products minus reactants. H2CO3 is negative 677.14. minus our reactants, so negative 393.51 plus the negative 285.83. And for this delta H, we should get 2.2, again, the units are given to you, kilojoules per mole. Okay, so those you should have already done before. They shouldn't be too complicated to do that. But if we need help, make sure to ask questions. All right, Hess's law. Hess's law goes with the 0th law of thermodynamics. Okay. So what Hess's law says is that the overall change in enthalpy for a reaction, for a chemical equation, is determined by piecing together intermediate steps. Okay, so if we have this A to B here, but we don't know what this number is, we can figure it out by adding together A to C and then going from C to B. So we can add these 2 together to figure out delta H1. Okay, that's also shown here. So if we have our reactants is carbon and oxygen gas, we can go straight to CO2 with this amount of energy. We can also do it in 2 steps. We can go to CO plus O2, that little bar there, and then we can go from there down to step 2. And you'll see these energies here, it's given the delta H2 and delta H3. If you add those together, so it would be the negative of delta H2, add those together, that will equal our delta H1. Okay, so energy is the same regardless of which path you take, but we need to this number may not always be known, so we need to add together those individual paths. Okay, so it'll look something like this. If we have this goal reaction at top here, but we don't know its delta H, and we have these individual 3 steps, we can figure out the delta H from them. Okay, so what we want to do is we want to have these become that by either multiplying the reaction, change the stoichiometry, or flipping the reaction, so making the products the reactants. Okay, and remember, was it up here? Yes. If you multiply the stoichiometry, you're going to multiply the enthalpy value. If you reverse the reaction, you change the sign of the enthalpy value. Okay, so for down here, let's look at NH3 first. For NH3, we have it right here only. So we need to first get this to be a 4. So we're going to do multiply by 2 for the reaction. So I'm going to do 2 for the reaction. That multiplies this number by 2 as well. And then we also need to flip it so it's on the reactant side. So I'm going to write flip. And if we flip, then we're multiplying the number by negative. We're changing the sign, the delta H value. Okay, so that's good for our NH3. We'll then have 4 NH3 on the left side. Okay, next let's do O2 is in more than one place. So let's wait on that for now. And O is only right here. So let's do that one. We need to do the same thing. We need to multiply this by 2 to get 4 NOs. That multiplies our number. But we don't need to flip it because it's already on the product side, so that's good. Okay. Let's do H2O as well because it's only right here. We need to multiply this one by 3 to get to that 6H2O, and we don't need to flip it. That's good as it is. Okay. So now let's go back to the O2. O2 we have in 2 places. Okay. We have here and here. So right now, based on stoichiometry, we have 2 plus the 3, we have 5 on the left side. That's what we want. So we don't need to change anything for O2. Okay, so if we change our reaction, right, if we flip the first one and multiply by 2, we get 4 NH3 goes to 2N2 plus 6H2. The second one, we're just multiplying by 2. We have 2N2 plus 2O2 goes to 4NO. And the third one, we're just multiplying by 3. We have 6H2 plus 3O2 goes to 4H2O. Okay, so if we do the stoichiometry here, if we cancel things out, we have 4NH3. Our N2s cancel out there. Our H2s cancel out. We have the 5 O2s, and this goes to 4NO plus 4H2O. Okay, this reaction matches what our goal was. We want to make sure that matches. Okay, so figure out your numbers, then do the stoichiometry, make sure that matches there. And now since that matches, we can do our math here on the right. So we're just going to apply what we had there. So if we multiply the first delta H by -2, multiply the second one by 2, multiply the third one by 3, and then add those numbers together, we get a delta H value of -906.3 kilojoules. Okay, so that's what Hess's law is. You're just piecing together the different parts to make a final reaction. All right, going to entropy. Entropy is a measure of how spread out the energy is. We're looking at how spread the energy is. We can also say how random or disordered it is. Okay, the units for this is typically joules per Kelvin. This image here, I like. It shows how the energy is transferred, or the energy is distributed. So these little squiggles are your energy. If it is all on one side, it has a low entropy. Remember, low entropy is less disorder. If it is more spread out, like it is down here, it's a high entropy, it's more disordered. So that's the energy between these bonds here. These are different bonds in the molecule. All right. This image I got from this video down here. That's a good video to see an explanation for entropy with in terms of energy. So if you haven't seen that, I would suggest watching that. That is linked on the slides there for you. But another way to think about it is just disorder. So if you look at these images down here, if these pieces are all put together, like it's a jigsaw puzzle, it's all ordered together. If the jigsaw puzzle comes straight out of the box, it's all broken apart, that's more disordered. Okay, same thing going from solid to liquid to gas. As you go across, the particles move further apart, so there's more disorder. Okay. So remember, more disorder means more entropy. So these things here increase your entropy. So it's going from solid to liquid, liquid to gas. If you dissolve something, if you're forming more moles of product, or if you mix liquids or gases together. Okay, these are things that increase entropy. All right, on a mathematical standpoint, we're going by the second law of thermodynamics here. We know that the delta S of the universe, so our entropy of the entire universe, is equal to our system plus the surroundings. And since entropy is always increasing in the universe, this is always greater than 0. Okay, so we're always moving to a less orderly state, right? We're going to more disordered. So that's why hot things move to cold things, or the energy moves from hot to cold, because we're going from more disordered to the more ordered area, so that overall we could be more disorder. Okay. Entropy, when we're doing calculations with this, we're going to use this equation down here. So it's the same thing as enthalpy, is products minus reactants. It's the exact same process. And remember, positive means more disorder, negative is less disorder. Okay, so we like positive numbers here. And then the last thing we're going to talk about is Gibbs free energy. Okay, you've seen this before. Remember this table, this is good to either memorize or understand based on this equation here. Remember, Gibbs free energy, the delta G, is spontaneity. If it's spontaneous, it'll happen on its own, right? If I put a piece of ice on a table, it just melts. That's spontaneous. Non-spontaneous means it will not happen without me actively doing something. To get water to freeze, I can't just leave it on the table. I have to put that water in the freezer. I have to take action for it to happen. Okay, so what this table does is, based on this equation, it shows you the delta H, delta S, that whole T delta S term there with a negative, and what their effects are on the delta G. Okay, so make sure you understand this table. That will come in handy with answering some questions about spontaneity. Okay, but let's go ahead and do this question at the bottom here. So if we have a reaction with an enthalpy of negative 92.22 kilojoules and entropy of negative 198 joules per Kelvin at 25 degrees Celsius, what is the free energy of the reaction? Is it spontaneous or non-spontaneous? A couple of things here. First, note the units. We have kilojoules and joules. We need to make them match. So let's leave things in kilojoules. So our delta G is equal to the negative 92.22 for delta H, that's in kilojoules, minus, let's skip our T for now. To put this into joules, we need to, to put this into kilojoules, we need to divide by 1,000, right? So negative 0.198 for the entropy. Okay. For our temperature, we have it in Celsius. Our entropy is in Kelvin, so we need to change it to Kelvin. Remember, to change to Kelvin, you add 273. So we get 298 there. Okay. And if you do that math, we get 33.186 kilojoules. Okay. Our number here is positive. If we have a positive number, then it is spontaneous. Okay. So on the AP test or AP questions, they can ask you a straightforward question like it is here, where if you're given numbers, you're solving for the Gibbs free energy. You can also be asked more conceptually like it is up here. So this isn't formed in a question, but it can tell you if it is a positive delta H and a negative delta S, What does that mean? Right, so you can either solve it by using the equation or memorize this table here. But make sure you understand it either way. Okay, so that is the end of Unit 6. That is the end of thermochemistry. We'll use some of this going into other units, so make sure we don't forget this. But if you have any questions or if you need help, make sure to come into tutoring, get the help you need. But aside from that, I will see you in class. Have a great day.